There we go. Good morning, everyone, and good afternoon to you in Egypt. This is very early for us and probably very late for you, so we apologize for the time difference, but we will make the most of it here and really appreciate your staying with us here. So, we're looking at how to create a um, robust EDA and IP ecosystem. And if you take a look at what's been going on in the industry these days, the future of chips is increasingly heterogeneous. For one thing, one application does not fit everything. One size does not fit all. There's a lot more customization than in the past, and there's a lot more problems in terms of it's getting more expensive. Yes, you can continue scaling down to the angstrom level, but that's going to be a very costly process, and there are very few chips that will actually warrant that kind of expense. That doesn't mean that you can't use a 3 nanometer or a 2 nanometer piece of logic inside a bigger chip that has many different components or inside a package, but it has to be done differently. The architectures are changing. Most of the gains are coming from the architecture in terms of PPA. Packaging is really important, and potentially materials are really important. So this is a fundamental change across the whole industry. What's needed from the EDA tool side to make this work, and how is that different from what we're doing today? Um, why don't we start this out with Bari Biswas from Synopsys?
Said, I hope you can hear me well.
Quite well.
Yeah. So yeah, indeed, the future of the chips is heterogeneous, and along with the customizations done by many of the product teams, semiconductor design houses, as you just said, Moore's law is slowing down, going to a few nanometers, and it's extremely costly proposition. But the design houses need to do this type of system, the heterogeneous designs, to drive differentiation in their competitive market. Before we talk about what is needed in the EDA tool per se, it'll probably worthwhile to the IC design itself is becoming multidimensional, multi-die, multiple process technology nodes assembled together. And in addition to that, some of them are done at a given point of time. Some of them are being reused from a previous generation that is being done. And the other thing that we are seeing on the design itself is, in addition to the traditional IC designers who are doing it, we are seeing those who are more with the system background. They are doing this type of heterogeneous chip. So for EDA industry itself, when you look at designs, this heterogeneous designs like itself, like this of kind, it's both a challenge and opportunity. It's challenge primarily because one needs to think of a solution that solves this grounds up, making sure that all the components that a system designer will need and IC designer will be there. The design environment should be seamless, going from 2D to 3D. So it should share some of the infrastructure data model with what we have done in the 2D design space, taking it to 2.5D to 3D stack, as well as it should allow architectural exploration at system level and address the scalability. I mean, I think maybe right now we might be talking about 5, 10 dies together. We need to build a system that would allow scalability up to 10 to hundreds of dies, and then deal with the connections that are between the system. And we have seen some of this protocol or the standards emerging very recently, but these are the key challenges and requirements for it. In addition to, very importantly, analysis like thermal and power analysis being done part of this type of a EDA solution that will have a comprehensive build grounds up and support this type of heterogeneous chip design.
Michael Jackson, what are you seeing? What's the big change here, and how does that affect what's going on in the development of the tools?
Actually, I agree a lot with what Barry. Can you guys hear me? I just want
Yes,
to
you're coming through loud and clear.
Don't want to talk for 2 minutes and then realize I was on mute. But I completely agree with what Bari outlined. I think one of the first things I'll say is just that today, it's worth noting that actually designs along the lines of what you're describing it, they're actually already being designed, 2.5D, 3D ICs. Certainly the future will be designing ones that are going to be more complex. I think from an EDA standpoint, for these 2.5D and 3D solutions, you need a host of capabilities, spanning physical implementation of the 2.5D and 3D systems, analysis, as Bari pointed out, and there's different types of analysis that are needed, connections with packaging and co-design. I think if you drill into it, you need to be able to do design planning for these systems. I refer to them as systems because they're bringing together these different dies, different chiplets, as they're also called. You need to be able to do the multi-design planning, deal with things like die placement, bump planning. You need a single database. We've already talked about the fact that many of these systems will be heterogeneous in not only in terms of the type of fabric. I mean, you may have like RF sensors, digital, but also in terms of the process technologies that are represented. And so you need a single database to represent the heterogeneous nature of these databases. You need, these systems are going to be big. They're going to sort of push the complexity envelope. There's needs for high capacity analysis, as Bari said, for power, thermal, 3D static timing analysis needs to be addressed, cross-domain ECO, and then there's the whole functional verification side of things. So really, in a lot of respects, I see, much of this is sort of an evolution of a lot of existing capability, adding the additional dimension, growing in terms of the ability to deal with the complexities. And the design of these that are being done today are generally being done by IDMs. There are initiatives that are underway in the industry to support reuse of chiplets, which will require some level of standardization. This reminds me a lot of the standardization activity that has taken place within single dies, but really sort of being extended to sort of this these multi-die configurations. And this will open the door for some companies to be in the game of supplying chiplets, for others to integrate the chiplets. And then there's also always a role for the custom silicon. So a long answer, but I think this highlights, many of the areas, where there's research and activity underway, where solutions are being delivered that will evolve. And it's an exciting time.
And given the complexity here, I don't think there are any short answers that are possible anymore.
Yeah.
John Lee, you've been talking about at Ansys a lot of this stuff for years in terms of the ability to simulate very large sets of data in order to understand what's going on inside. What's changing there? How much is still needed? Do we need more? Do we have enough now? How does this work?
So I'll echo some of the things that Bari and Michael said. And what you said, Ed, right? There's been a continued challenge as you see a foundry like TSMC offering new process nodes like 3 nanometer. And so capacity, speed are a big challenge. If you look at reticle size die, like an AI chip or a GPU that uses the full extent of a single die. But now as we look at integrating multiple die using silicon interposers or stacking die, the problem becomes immensely much larger, as you're saying, right? I think that's obvious. It's also important to note that these are early days, whereas I'd say every high-end customer, many others are doing 2.5D or 3D ICs. It's just at the beginning of what the potential is. And so the tooling and methodologies are new, are challenging, and require close cooperation between a company like Cadence, Synopsys, Ansys, and the end customers. The one thing I'll highlight is what's happening is the lines between system and silicon have blurred. So whereas before you would have the heterogeneous capability through multiple chips and multiple packages on a PCB, Now we're able to integrate those all into a single package. And so, whereas before you had a system designer looking at electromagnetics or looking at signal integrity or thermal integrity, all of those analyses need to now be done in the context of multiple die. And so the challenge here is now you have traditional chip designers who are very familiar with EDA workflows, but now we have to bring in a thermal design team or thermal analysis team, an electromagnetics analysis team. And so new methods and new tools and new physics need to be brought into this 3D IC workflow. So it's a challenge, also an opportunity. And I'd say we're still in early days that would look back in 3 years and say, okay, now we have a better understanding of how this should be done.
Sean Varshney, a lot of this has been, we've been talking about moving all this into the cloud and doing a lot of the EDA in the cloud. The reality is we haven't quite ever moved there en masse simply because nobody's been able to figure out a business model that works. What's changed there? How is this actually going to come together, and do you foresee a fairly large role for the cloud in the future? Prashant, we're not hearing you.
Okay, can you hear me now?
Yeah.
Right, awesome, thank you. So yeah, absolutely. I think what the statement that you just made, I would say this was absolutely true. If we just rewind to 2.5 years or so, back in 2018, TSMC announced the Cloud Alliance, and that's when they announced that they are moving their 5 nanometer simulation at that time into the cloud. So that was kind of proving to the industry that the security that the cloud offers, as well as the performance that the cloud offers, is starting to get there. And that was spurring a lot of momentum in the industry overall. The interest in cloud had been gaining a lot of momentum. And we saw in 2020 and through even 2021, folks just trying things out, right? I mean, just basically getting more comfortable. As this sounds interesting, it looks promising. Let me see if the security audits from my InfoSec perspective are in line or not, or whether the cloud is actually going to provide me the right performance levels or not. So we are through that now, and if we start to look at mid 2021s and coming into 2022, the customers are starting to make big decisions. The customers are starting to make migration strategies on how they can get into the cloud. So I do believe that the change is happening already. I think if we were to ask this question a year and a half ago, like I said, I think we would just say yes. People are still trying to figure things out, and maybe it'll work or maybe it will not. But I think we are over that. At this moment, everybody is looking at a 3 to 5 year strategy on how they can move majority of their workloads into the cloud. Of course, I mean, just getting to the smaller geometries is one of those things that's spurring this discussion all over again. And if you're looking at 5 nanometer simulation, or 5 nanometer SoC design in general, it takes anywhere from 5 times to 10 times the number of hardware resources to be able to do that compared to a 14 nanometer or a 16 nanometer chip. So a huge amount of resource requirements, and the folks who are getting down to the smaller geometries because of the reasons that other panelists just talked about, they are all struggling trying to figure out how they can augment their capacity in their on-prem data centers. And that's just not easy. It's not possible. You've got to create a new data center. You cannot add capacity anymore. So that's the forcing function for folks to now decide that, either if the cloud works, if the cloud economics and performance and security does work, then that's a viable solution. And if it is, then might as well just move over. So that's, I think the industry is sort of at the cusp of making that decision. So even though right now you would say the cloud market share in the semiconductor industry is probably in single digits, maybe even lower single digits, but it is gaining a rapid adoption at the moment, and we will see this over the next 3 to 5 years. Majority of the on-prem capacity or on-prem workloads will be moving into the cloud, barring some obviously sensitivity on the data on what has to reside on-prem. The large set of workloads and large set of work will be moving into the cloud.
Aitken, from the IP side, what do you want to see in the tool chain in the future that isn't there today?
It's an excellent question. I think the other panelists have touched on it a little bit, so that there's a need for effectively tools that operate across multi-die solutions and not just take them into account to say, okay, I have this here and I have that there, but are actually able to allow you to co-optimize things. And that level of how should I partition my design? What actually should go here? What should go there? How can I validate, other than making some PowerPoint or an Excel sheet or something? How do I figure out what an optimal way of doing that is? And that part is a part that I think is, in some ways, it's chicken and egg thing from the tool supplier and from the company standpoint. It's like, how do we know what the partitions look like? Well, we don't really, because we're not entirely sure what the 3D technology is supposed to be, and we're not sure what the boundary is. And another point that hasn't been brought up yet, but is really important, is how do we create an abstraction of a chiplet that's actually stable across design in the way that, say, a SPICE model or a characterized standard cell library is. It's an abstraction that you literally go to the bank with and say, if the silicon meets this, then that's good. And if it doesn't meet it, it's the manufacturer of the silicon's problem. If the design works and or if the design doesn't work and the SPICE model says it shouldn't work, that's the designer's problem. If the SPICE model says it should work, that's the foundry's problem. There isn't that level yet of a boundary. And that's why we see in all the solutions, I believe, that we've talked about so far, the same company is on both sides of the interface, because that way you can manage it. But if you're going to have some kind of a chiplet ecosystem where there are multiple companies, somebody supplies a chiplet that does this, somebody supplies a chiplet that does that, what is a level of abstraction of those things that allows you to actually work with them and create a system? And so tools that define what that abstraction is and then use it is something that is really, I think, missing at the moment.
Mohamed Elmalaki, I think I've pronounced that right. From Intel's perspective, Intel has been working with a very heterogeneous design for quite some time. You've got all sorts of chiplets going into some of these designs. You've got an architecture, you've got your own NOCs. You also have some of your own tools that you've been developing for years and have used traditionally. What's missing out of the commercial flow these days that you would like to see, and how will that change what you're doing?
So I would mostly agree with the other panelists, like on the points they brought up, the existing EDA tools. It is not like we wanted like a breakthrough. It is an extension of existing tools. Like I'm not seeing like a specific tool missing, rather than like a scaling, larger scale. Like, the thermal modeling has been like an issue. I think that's something that can be like improved. The challenges that comes with mixing processes, not only like have chiplets like all on Intel process, right? So we have or like the industry in general have designs that have chips that comes from like TSMC or Samsung or Intel all going on the same package. So this is all like new things, right? And I would say also like, different companies have different packaging solutions, like for the chiplet assembly, like interfacing between chiplets. And like that will introduce a challenge when you try to have a chiplet ecosystem like Rob was mentioning. I would say like if we look at the EDA vendors as also an IP design houses like that provide IPs that we use, I think IPs around chiplet interface are a major thing. Like, if we can standardize those interfaces, like have innovations in terms of compression, how we transfer data, how we sync things like, clocking and DFX, like, and things like that across chiplets, I think that would be very helpful. CXL standard is promising, and it's like, you know, being used a lot, like when we interface chips. But I think there's like a space for innovation in how to abstract the level above the basically inter-chiplet connections. So that is something that I think will help a lot. I wouldn't say that the EDA part is the most challenging. Like, I think there is also like the software, like the software part is very challenging. Like, you know, how can you actually manage, you know, software across like heterogeneous chips? And you know, for the industry as a whole, this is one of the most gating items, right? And I would say like we came a long way in the last like 2-3 years in how we assemble chiplets in a package. I wouldn't say we have done the same improvements on the software side.
So let's build on that a little bit. What do customized designs look like in the future? Are they collections of standard IP, semi-standard hard IP like chiplets, or is everything custom silicon, which is really what it's down to right now, or is there some mix of the two? Actually, let's start. Mohamed, why don't you start there, and we'll work our way backward.
Okay, so I think it's like, you know, at a high level, it's like a regular cycle, right? Like new workloads comes in, like we build like, you know, very custom accelerators to catch up with the workload, and then you know, by time the workload itself like stabilize, and then it moves from like being like, you know, a fully custom, like, you know, purpose built like IP or an accelerator to general purpose. I think with the like the biggest example we have now is AI workloads. Like we have a lot of like real small custom accelerators for AI workloads. And we are building like custom silicon for it, custom chips for it. But we could see like a shift to general purpose CPU or general purpose GPU as we go, as the workload like, you know, stabilizes and things like that. People like rely less on fixed functions. So it is a mix, and it's a regular cycle. Like we'll always have like, you know, custom, like, you know, special purpose built accelerators or silicon, and you'll always have the general purpose. And the game is like, you know, how much of that can you move to general purpose so you can have the same piece of silicon that does a lot of things. Sometimes you can, sometimes like the media case, you still like, you have to still live with like, you know, fixed function accelerator if you want like performance. But that regular cycle, like the future, I don't see it any different. I see a mix between like, you know, fixed function and general purpose.
Rob, what happens on the IP side?
It's an another excellent question. If you look at the history of IP 20 years ago, there were a whole, you know, there was this whole question of should we have hard IP blocks, which are just effectively GDS that you drop in a chip, or should we have soft ones that are synthesized into a fabric? Those kind of evolved over time into what was essentially soft IP that was built according to a recipe, because that was the most economically sensible way to get things into large chips. When you switch to multi-die, that decision might change, because it might actually make more sense to have something that's closer to an or to a hard IP, which is what a chiplet would be effectively. And you lose the flexibility. Say if you had a multiprocessor system that had 16, you know, you could dial in, I want to have 4 cores, 16, 32, what have you, and I want them on a little block, and I just want that to plug into my system. Defining what that block is and how it connects to the rest of the system, if we could come up with a standardized way of building such things and for them to connect and communicate to broader systems, that would simplify a lot of the design effort that Prashant was mentioning earlier, where you have huge amounts of effort going into verification of something. If that block, that chiplet is predefined, pre-characterized, and pre-verified, you don't need to do that anymore. But you do lose the flexibility of, oh, I changed my mind. 16 wasn't really enough. I wanted 24. You know, too bad. It's too late now. So, or maybe if the edge, the boundaries are defined on the edge, maybe you could actually swap that in later and make a decision. So there's if you can get all of the standards that we were talking about and all of the packaging constraints, thermal constraints, die ownership, et cetera, solved, then that opens up a path for a chiplet ecosystem. But getting it to work really requires giving up on a certain amount of flexibility in exchange for some predictability and hopefully some cost savings. So yeah, I think there's definitely an opportunity for that to exist, but there are a few problems to be solved first.
From an EDA standpoint, can you use the same tools for a one-off low volume design as for a high volume mass production design? One of the big things that's happening right here as we go forward is we used to think about developing the next node for cell phones or the next computer. What's happened is everything is now some collection of customized silicon. It's going into much smaller volumes. So, Michael Jackson, from the EDA standpoint, how do you deal with that? What kinds of issues are you wrestling with?
Well, first of all, to this general question, Ed, I agree with what Rob and I think it was Mohamed had indicated that there will be a mix of both custom design and reuse in these systems, just as there is a mix of them today in a single die, and both will need to be leveraged to address the overall system requirements and design objectives. I think in terms of the fabric that is going to be more customized, there's going to be certain tools that are going to be used for that. If there's some processor type application and it's all custom, then you'll be applying one methodology. If you're going to be using some of these reusable components and chiplets, you'll be effectively taking them and then integrating them into the overall system. So I think a lot of the same tools are being used in both scenarios, and they're both needed in order to pull together the overall system.
Barry, from your standpoint, do the tools that exist today, do they cover the whole wherever we're going in the future, or do they need to be updated, enhanced, changed out?
Ed, I think Michael summarized it well. The same tool we foresee will be various pieces of this heterogeneous system, as described by Mohamed and Rob. But what is different is methodologies. The methodology will need to be different depending on the different types of design. And similar to what Michael was saying, whether you are doing processor cores, whether you are doing a low power design, whether you're doing IO, there will be different methodologies that would be used. Some is custom heavy, some will be much more digital oriented. The methodologies will be different, as well as integrating all of them together, including the protocols or the standards that are connecting this heterogeneous chip system. And that connection between this heterogeneous chip system is, I think, of extreme high importance, because there are IPs that are going to be created to connect them. And what methodologies are we going to use to analyze or design each of these chiplets or units by themselves and together? And so where I see the change required will be in terms of methodologies, not the fundamental tools themselves or core algorithms of the tools that are being used there.
John Lee, Ansys has been wrestling with a lot of the physical effects for quite some time now. How do you see this rolling out? Because we are starting to deal with potentially unpredictable physical effects that we've never seen before: power implications, thermal, noise, all sorts of noise, actually.
As I said before, we should think about it as the lines between system and silicon have blurred, and so what we traditionally would margin or guard band at a die level, we can no longer do that. So if you're taking logic die, but then you have memory die to bring compute and memory closer on an interposer, or if you add in RF communications on a separate die, or increasingly silicon photonics and electrical compute together within an advanced package, you run into a tremendous set of problems, right? You run into now electromagnetic interference between the die, where you have a bus line and it may unintentionally switch because of inductive coupling either on that die or from adjacent die. The thermal integrity issues are real as you put multiple die on an interposer, and then that can induce, power begets temperature, and then temperature begets mechanical stress and strain, which can affect the reliability of the part. So to answer your question earlier about bespoke, custom silicon versus more standard, and low volume versus high volume, I think it all comes down to context. Increasingly we're putting such systems into automotive, very harsh environments, but also requiring very high reliability. And so, to Bari's point, these methods need to evolve or need to be strengthened in order to ensure the electronics reliability of those systems. And the challenge here is that you may be designing all of the silicon yourself, in which case you have full visibility. But what happens if you're getting a die from a supplier, and that supplier doesn't want to give you all the details of that chip, right? That's the IP, the GDS, the schematics. But then how do you ensure thermal and electromagnetic reliability, as I was talking about? That's a big challenge.
When we look at some of these complex designs, and I always tend to throw verification into the design process, even though the verification guys will always yell at me going, no, it's not, it's separate. But reality is verification, debug, those types of things have taken probably about 70% of the design time, the design cycle. What happens as we move forward and we start getting into the heterogeneous world? Does this go up? Does it become even more complex than it was before? Because A, we are doing much more customized designs, and B, we're using potentially off-the-shelf chiplets or other devices that have never been fully characterized for whatever they're supposed to be in, whatever they're going into in the next generation. Is this going to require more brute force computing to do more simulation, emulation, and analysis than it did in the past? Prashant, why don't you take a whack at that?
Sure. I can definitely answer the question from the infrastructure perspective. Clearly, this is kind of what we hear. The number could be anywhere from, let's say, 50% of the design cycle to 70% of the design cycle, depending upon the customers. But it is absolutely right in terms of the compute hours that are spent on doing an SoC. That's kind of where the distribution is. So from our perspective, as a cloud vendor, we are starting to also look at verification as a standalone workload and trying to see how we can optimize that infrastructure or reference architecture that's required for executing this workload, and do that for this generation, and also work very closely with the EDA vendors to kind of figure out, where are we heading towards and how is the architecture now changing going forward. There's a lot of that discussion and slicing and dicing of the workload itself that's going on right now, both with Cadence and Synopsys, much deeper analysis on that to try and optimize not just the software algorithm, but also start to look at infrastructure as a dimension to optimize, and start to now look at new cloud technologies and caching mechanisms, and how are we doing, for example, memory management and storage management in the cloud, and the data transfer even from on-prem into the cloud and back. How does all of that kind of play in when you're looking at a verification workload? For example, we know in a certain hardware architectures are actually more suitable for running verification workloads. So the AMD new architectures and some of the Intel architectures has been really great when it comes to single CPU performance. But then if you look at a couple of other platforms, they are starting to also look at L3 cache, for example, started to become more important on how efficient this workload is running on a hardware architecture. So those are all the same thing in the storage as well. We are looking at high performance network storage. NetApp appliances, for example, they work really, really well for verification workloads. So just starting to think on what would be the right appropriate reference architecture, even if customers are picking a hybrid configuration where their data is, let's say, in an on-prem environment, and they want to use cloud for compute. What does that scenario look like? How to play that out, and enable a on the fly data transfer, be able to package the workload and run something in the cloud with some sort of a caching mechanism so that you can still have an efficient run in the cloud and then be able to analyze the data and pull things out into on-prem. So yes, absolutely. We see, like I was saying, infrastructure as a dimension of optimization. We are working very hard to introduce new technologies to try and keep it on that track, but then also working very closely with the EDA vendors to see what we can do together. So this is where hardware, software, co-design, we take it to the whole different level where we look at EDA algorithms and infrastructure combined and how can we improve the overall execution and how can we optimize for the overall performance.
Barry, when you look at this, this is pretty much a brute force approach. Is there a more elegant way to do this, or are we just going to just crank up the clock cycles on the emulators and run for it?
So first, I think as Prashant described, various ways, even within when we say brute force approach, let's take a bigger problem and start solving it by looking at it in a very more intelligent way of how a software algorithms matches with the hardware. So one good thing about functional verification and also the emulation space is inherently a parallel problem. Distribution of it on not only multiple cores, multiple system, but being able to use some of the say spot instances within the cloud system, leveraging those, being able to get the scalability that is required is there. But having said that, as we go to this heterogeneous system, I mean, we can imagine this to be today's single die with like the hard IP now becoming chiplets, and then we just scale it there. The scale is enormous. So we will need to also think of other ways to essentially divide and conquer the problem. Either one can call it a hierarchical approach, distributed fashion of both simulation as well as the debug problem itself. Actually, we should be thinking about the debug as an extremely critical piece of it, because without debug, all the verification simulation results, but we won't get the insight that is required to further improve the design and prevent bug escape. So one of the things that we are seeing, both driven by heterogeneous design as well as what we would see on a single chip, is we would need throughout the verification tools take advantage of the data being produced through each step, so that we have something that is an AI augmented technologies that can be added on top of this data to make much more better in terms of coverage closure, in terms of the analytics and the debug that comes out of the verification and simulation products. That will reduce some of the brute force approach that is being done for in terms of the simulation, and bring intelligent verification into play. So that's how we see it as it goes into the future.
Michael, same question. What changes?
I think everything that's been said so far, I do agree with. I think your question started with, is this going to require more brute force computing? And I think the shorter answer is definitely yes. I think these, tomorrow's 2.5D and 3D systems will place obviously greater demands in terms of functional verification, especially in terms of capacity and performance. And it really does this in other aspects of verification too. We're talking about functional verification here, but the other aspects of verifying the design as it relates to thermal, power, integrity, timing, we're seeing an explosion in complexity there. And so there's going to be a need to leverage the various simulation technologies. They're going to need to evolve. Emulation is going to be playing an important role. The complexity of the system is going to demand, is going to pose questions in terms of how you verify things, in terms of like, where do you get the vectors, right? And the best way to do that today is with emulation. Can run thousands of times faster than can be done using just standard simulation techniques. So being able to boot software earlier in the cycle is always important. It's going to be important in these kinds of systems, but being able to do that in a system that is so heterogeneous that may have fixed die, you know, as well as custom silicon, is going to be, you know, there are going to be problems that need to be, you know, addressed and solved to enable all this.
John, we've seen in the past, going back several process nodes, the margin that the foundries used to build into the processes they had typically soaked up almost anything that we had as problems. So they would fix power, they would fix some of the layout issues, and they had enough play in their design rules in order to be able to do that. Over the past several generations, that's just shifted far left, and now it has to be done much further up front. What impact does that have in terms of the tools and what kind of how much processing needs to be done up front there?
It's made the problem a lot tougher, Ed. You know, if you think about even a single die and a single die pumping in 400, 500 watts of power, and at the same time, you want to operate at low voltage and you know, run off of a battery as much as possible. You know, those are conflicting challenges, and the answer, right, if you're running at low voltage and you have you know, massive die, massive compute, and then you have noise that comes from power integrity or from, you know, other sources of noise, other die, for example, you need to have much better coverage, right? You can't guard band to really design. You can design if you don't have the right coverage, then you have to guard band. But even guard banding, you know, margining is not sufficient, as you know, we've seen that the complexity of multi-physics as you know, timing and power and thermal, electromagnetics all interfere with each other. It's hard to come up with a, you know, a reasonable guard band. So the answer to this is better compute, better coverage, right? Better mathematical methods. AI ML is certainly you know, one of those, but there are a host of other methods that we're bringing forward to help solve that. And you know, to address the question earlier, you know, ultimately to do everything flat and brute force, you know, the cloud provides us an opportunity to do that, but that's not practical. And just like in all other phases of you know, designing chips, we've developed methods of abstraction, of modeling, of, you know, hierarchical approaches. The same now needs to be done across multiple die. And in the context of the problems I've been talking about, you know, there's a need for multi-physics models that abstract a die in a sufficient way that gives you enough resolution so that when you look at across multiple die, that you can really look at these multi-physics effects. And that's a challenge, something that, you know, both in terms of research as well as you know, practical development, there's a lot of work ongoing today.
So, Mohamed, is the solution here to come up with a fairly standard way to put all these different pieces together? Maybe one that is 80% good enough for most of the market, or 90-10? How do you actually break that down? What do you see as the future here? Is it all going to be customized, or is there going to be some sort of standardization here?
I think the answer is like product specific. Like there is still markets that will benefit from a general purpose. Like, you know, when you put a product that fits 80%, right, and the 20% will be running at like a lower, like, you know, KPIs more or less. But for other markets, chip vendors in general would make like customized solutions at like 100% optimized for them. So there's no, I'm not seeing like, you know, following the same, you know, pattern. I'm not seeing like the future will carry something different. I think we'll still, like, you know, being like, you know, put chips in both. It depends on the workload and like how the workload is stable and how, like, you know, how big the market is.
From your standpoint, we've been looking at, well, you think about an ARM chip, it's very well characterized. You've done a spectacular job of running it through as many possible scenarios as it can possibly be run through. This is now going to be combined with a lot of other chiplets and other components that really have never been characterized in this way before. They running at different densities, different package approaches. How do you see this unfolding? What sort of issues do you foresee?
I think you kind of outlined what they are, that when you start merging these things together, they'll be used in ways that the designers didn't think of, and that things will start to break. And I think an approach that we're going to have to start incorporating in a much more mainstream way is resilience. That architecturally, these systems are going to have to recognize that things can go wrong in them, they will go wrong in them, that they need to be able to react to them. And that sort of splits the verification problem into two classes of essentially things that will break the system if they happen, and things that are bad if they happen, but can be worked around as long as they're identified on the, in time and then dealt with. And there's a whole multi-layer abstraction to that as well, too. You can put that in the software so that the software understands that if it asks for a non-time sensitive computation and that computation doesn't happen for whatever reason, then it just re-asks. That's the simplest time redundancy approach, but there are many more. But the validation problem, I think, and verification problem is essentially an economic one. It's that people spend 70% or whatever it is of their budget on it because that's kind of what it takes to get a chip out the door. If it switches so that looks like 95% of your cost is now verification and 5% is design, that's not really sustainable. So we'll have to think of better ways of doing it. Either instead of throwing just brute force simulation and hoping for the best, actually deliberately targeting algorithmically what might actually go wrong. What is, of the billion things that I'm simulating, which of these things are more likely to happen? And that kind of thing already exists in circuit design. People play with tail distributions and they go and look at, they don't just throw random Monte Carlo simulation at stuff. They actually look at what might fail and what would happen as a result. That same sort of process has to happen in systems. And then going back to your original premise for this question, the ARM does spend an enormous amount of time validating and verifying processors. Other people who want to play in chiplet space are going to have to put similar effort into verifying their stuff, or nobody's going to use it.
Hopefully.
Well, they'll use it once, maybe.
We've been talking about software-defined hardware in this industry for a few years now. Is this the same as the old hardware-software co-design, which I think goes all the way back to the days of Intel Microsoft, where it was the old Wintel duopoly? Has something changed here? And if not, what will make it work this time around? Because we've run into problems in the past when we tried to move this beyond just two vendors. Why don't we start out with John Lee?
I'll share, the perspective from, our experience. It's somewhat cyclical as we look at, going to full bespoke silicon designed for, custom applications, to the use of software-defined architectures or, architectures like FPGAs, right? And I think we're working through, what the right balance of bespoke or custom silicon versus programmable is. And certainly, 2D IC, 2.5D integration allows for a good richness with that. The problem is, I think it's been stated before, is not just it's not just the silicon or the device that matters as much as it's the software that goes along with it. And the challenge that we see in this area is, the dynamic thermal management, where you're designing silicon and you want maximum performance, but at some point you need to throttle back that performance because temperature limits are being exceeded. And if you don't do dynamic thermal management properly, then the performance of your system may be substandard, right? A good example are your mobile phones and how efficiently, or the new M processors from Apple and how they're able to efficiently operate at high speed while managing thermals. So the only way to do that well is to understand what the real workloads are, which are the software itself, and then using emulation to boot up and run a complete workload. And so it is something that's extremely important. I think AI ML techniques will play here. But this is one of the big challenges that ties in with verification. There's a lot of software related work, and the cost to our customers, the software side is probably much more expensive than the actual physical design side.
Took me a second to remember that we have both Intel and Microsoft on this panel, so
They can probably comment.
let's go right to the horse's mouth here. Mohamed, how does this all change? I mean, what happens? Who's in control these days? Is it the hardware? Is it the software? Or is it some combination of both? And how do they really interact over time?
That is a good question. Like I think like if I go back to like your original question, like the software defined hardware, right? And it was like very popular in the early 2000s, and it didn't make a breakthrough. Like it kind of like died out a little bit, and like there were startups and like some movements early days, but it didn't work out. And the conversation is brought back to light because of the AI ML workloads, right? Because like you design a chip for an AI workload, and then 3 months later everything changes, right? You start with like metric centric, and then like you find out things are shifting to like 40% of the workload is nonlinear, and then you optimize for that, and it moves back to like shallow like layers versus like deep layers. And like just a simple switch in how the AI workload is designed cause efficiencies to swing really bad. So hardware engineers cannot catch up, right? So definitely, in general, software is in control in this part. Like I would we would gladly admit that, and we are trying to catch up. So that actually brought up the software-defined hardware back into the conversation, right? And starting from the early architectures of having like big compute elements, and you try to reconfigure at runtime like the interconnects and the memory allocation. So that was like the classical software-defined hardware that actually goes like all the way down to like an FPGA where you have like smaller elements and you start like to play with it. I would say that on the FPGA domains, this is becoming more and more relevant. So they will take a workload, they will compile it, and not really like take designs or gates. Like they don't take RTL and compile it. They will take like an AI workload, a software AI workload, and they will actually put together an architecture that will run that workload most efficiently. I think this is like the closest thing to a successful software-defined hardware that we have. And then there's like a hybrid approach where the FPGA itself will have bigger resources like processors and like small AI accelerators and things like that, and the software will still not look at RTL, will look at the software and then basically put together a solution for it. So I think it's like this is something that is changing and will change in the future. It is something like I'm most excited about, and I think the future is carrying like a picture of tool chains that compile software and basically allocate resources and reconfigure programmable hardware on the same chip. So chips with mixed programmable hardware and hardware resources, that actually is something that I think we'll see more and more coming forward.
And Prashant, from your standpoint, you're looking at running some of this stuff in the cloud. Where are you seeing the overlap here between the hardware and the software? Which one's demanding more cycles, and which one's coming first, and how are you putting them together in a much more tightly integrated way?
So I think if we look at how in overall hardware development life cycle, I mean the market conditions are such that there is a need for the for the customers to start kind of putting chips out at a much faster pace, right? And so the design cycles are shrinking, and therefore there's a pressure for folks to try and figure out how can they quickly do some prototyping work, and that prototype needs to convert into a hardware pretty quickly. I mean, there are already some EDA tools out there. They even promise, starting from the C models, you can just directly go either into an FPGA implementation or go to an ASIC implementation, etc. So those are all the concepts that can help you kind of quickly prototype and get something out quickly. But what we are observing is that over time in the life cycle of that hardware, there would be a need to optimize that further, right? So once you start to do things fast, they are not as optimized as something that you would do custom and take time. This is why all the custom CPUs, custom ASICs took a long design cycle, because you are squeezing out every little ounce of power, every little performance that you could from architecture perspective, also from implementation perspective. So there is a trend to do things fast and quick just because the market requirements are such. But over time, there is a need for us to again go ahead and do this optimization, because then if you have to go to mass volume, you have to optimize the hardware. So typically you would say A0, A1, our initial silicons are going to be our quick prototypes. And then over time, you would see design cycles again expanding depending on how successful the product is out there. This is what we see from our side as well. And this is where we see our customers spending a lot of compute cycles to do this analysis. How quickly should they be expanding? How quickly they should be making a decision whether or not to invest in an optimized hardware or not. So that's the trend we see.
The other three guys on this panel that I haven't hit on here all develop soft IP, which is somewhere in that netherworld between hardware and software, and you can adjust it as you need to go. How does that play into this? Is it more flexible? Do you start seeing the IP beginning to change as time goes on here to whatever you need? Do you adjust that, and can you adjust it that easily, or is it still going to be, this is the IP that we have, and now we have to work with this and all the characterization that's been done and all set in stone as you go forward? So Bari, what's happening? You guys do the ARC processor. What changes there?
So not just ARC processor, we have there's a whole rich set of IPs. I mean, if you even look at the PCIe, the controllers and the PHY that goes with it, high degree of configurability. And there are two levels of configurability on these software IPs or soft IPs. Either as they are produced in factory, as they get shipped, there is a configurability with that, as well as at customer end. When the users are integrating it into their design, they can configure in how they would like to harden it, as well as Synopsys comes in and customizes it for them. So definitely, Ed, from the perspective of the IP design. I wanted to go back to the original question, as well as Mohamed's very well described software-defined hardware. And as he pointed out, the reason it came back is the AI workload. And this is a promise, and I'm glad he's very excited about the future, because I think these are the amount of workloads on the cloud that Prashant and the team is running at Microsoft is increasingly AI workload. Would like to see our EDA software taking advantage of the software-defined hardware. There are challenges, as some of you might would know quite well. There is an initiative of software-defined hardware with our US DARPA part of that program. So our verification team actually got involved and shared an experience with me when I was asking them about this topic. So one of the key challenges there lies with the compilers that are created, with the programming languages that are going in. And what they found is to be extremely complex to get our verification softwares, all our AI workload mapped into the software-defined hardware. So we do have a challenge, but we have also an exciting opportunity there, because if we can do that, then on the fly, depending on what are the AI workloads, our hardware can self-configure itself based on the needs. So definitely looking forward to this driving our roadmap on AI workloads.
And Michael, Cadence has been building a lot of programmability into the DSPs it's been making for years, almost from the beginning, largely because there are so many changes and that are needed out in the marketplace, and there's so much demand for customization. How will that play into some of these complex integration schemes as we start getting into advanced designs with chiplets, with multi-processor type of implementations? How do you see all that changing?
I think that I think it's important. I mean, the configurability, you know, it really sort of facilitates the use and the application. And this will be an important role in, say, you know, creating the IP that would be hardened to form sort of the chiplet. And maybe you know, subsystems within a chiplet. It depends at the level at which the chiplet sort of exists. So we see this notion of configurability as being important, not only in terms of single die applications, but it will also be important in the multi-die.
And Rob, from your standpoint, do we just have more specialized hard IP processor cores, or do we have some sort of programmability built in there?
I think this is a case where you wind up with effectively both. So from the processor side, there's a desire to have, you know, all of the configuration options and so on that people like, but there's also an idea of, let's just have a platform. I want to have a standardized structure that has, you know, a whole bunch of processors that, say, in an automotive world, for example, these ones are all dedicated to general purpose processing. These ones over here are dedicated to real time and safety. And here's a software platform that ties all this stuff together. So that kind of thing, I think, is part of the answer. But I think the AI workload piece allows for some really interesting optimizations and customizations that are very nascent at this point, but that could be developed out of the component pieces that we have. So for example, if you're thinking, how is it that I'm going to optimize this AI algorithm that I have? One way that you can do it is you can recognize that, say, an emulator or a giant farm of FPGAs in the cloud is effectively an excellent platform to work on that problem. So you can distribute your problem across this thing, develop the solution for it, and then say, oh, this solution is cool. Now I'm going to map it to my chip. Then you run into the problem that I think it was Mohamed brought up, but several others as well, that this is dynamically, your workload changes over time. Now what? That's a case where you want your custom accelerator to be capable of recognizing changes in the workload. You know, at a simple level, maybe it's a change in the sparsity of your data, and being able to either reconfigure itself, or if it's a chiplet-based thing, use a different part of the chiplet to solve the problem dynamically, that this week's workload is sparse, next week's workload might be less sparse. Figuring out how to build systems that are capable of that is a really interesting and open research problem, but the tools to do it are out there, and the physical objects that we need to solve it will be out there. So I think there's an opportunity there. There's just waiting on someone to solve it effectively.
Okay, let me give a follow-on to that one, Rob. What does a chip look like in 5 years going forward? And does that chip in 7 years, the one that you've created in 5 years, still look the same, or is it a completely different structure?
Prediction about the future is always challenging, right? So I think a chip in 5 years, or a packaged object in 5 years, is going to consist of some relatively standardized components of, here is a memory system that contains large amounts of memory that's accessible on latencies that people like. Here's a set of standardized processing elements, CPUs, GPUs, what have you. And here's a blob that, you know, that effectively implements what I was talking about a minute ago. That's something that's able to handle the AI workloads that we can likely anticipate exist in 5 years, because if we're going to build these things 5 years from now, we need to start architecting them now. And that is able to adapt on the fly to changes in what its input data look like, and that structure is standardized enough that people can build a software platform and software stack around it that allows people to program that thing. So for such an object to exist and be economically viable, we're going to have to answer a bunch of the questions that we talked about earlier. But I think one of the key ones is going to have to be, it's going to have to be resilient enough to be able to adapt on the fly to thermal challenges, adapt on the fly to errors of various kinds that pop up, and have at least enough capability to let people know where if it's observed to be failing, where it's failing. So there's a whole bunch of stuff that goes into that. The 7-year variant of that, I'll go with more of the same now, but works better. But I'm sure there'll be a better answer in a few.
Mohammed, you guys have got to be wrestling with the same issue, right? What are you looking to design in 5 years, and how will you adapt to it as it starts changing in the real world?
So like as Rob was mentioning, like right now we're architecting the chips that will come in 5 years, and any Intel panelist you will invite is trained not to answer those questions, like not to expose them. So I'll try to work around it, to be more generic. But I would agree to Rob, right? It's like data intensive. I think this is the biggest challenge, right? You have a small limited power device on the edge that have to process unbelievable amount of data, and in very limited power envelope, and that spans a lot of new architectures. We have teams in Intel Labs working on it. It's processing connectivity, and the balance between what runs on the appliance versus what runs on the edge server. The shift to the metaverse, which actually even started before the Facebook push, introduced all kind of challenges in this area. So we have ideas. I think other chip companies have ideas of how that will shape. We have all of us have technologies in the lab that we are developing for that. But I can say it looks very different, from what we have now. It's a very it's not an easy to solve problem, and it's I wouldn't say that anyone have a solution to process this. The simple problem statement is huge amount of data that have to be processed on a small form factor with a limited power, and you can imagine the amount of solutions and research that's going into that right now.
This has potentially huge implications for EDA too, because now you're working off of designs that are going to be A, customized, B, you don't know how they're going to age over time. You've got a lot of different components in there. You've got all the physical effects that may crop up. You've got always on circuits. You've got potential interactions that can come through over-the-air updates. What do you have to do in terms of the tools in order to be able to create these chips that will work over their expected lifetimes? John, why don't we start with you?
Maybe not specific to EDA, but and tying into the previous question. I mean, things that are happening now that will become more prevalent in the future are, on-die sensors to monitor what's actually happening on die, and it ties into the resiliency that Rob was talking about, and that will become increasingly important as we look for increased reliability from these products. I think another trend that we see happening is electrical signaling, right? If you push data faster and faster, there's a power wall that happens, and so increasing use of photonics will be necessary, and co-packaged photonics we think will be very prevalent in the near future. And then there's some other alternative computing techniques that maybe in 5 years to 7 years we'll be looking at quantum compute in certain applications, and that could be groundbreaking, and there are various approaches involving low temperature compute as well as even photonic compute. So I think what net what this means is it's I think as one analyst calls this, an indispensable nature of EDA, that the challenges that are in front of us, and from a research standpoint, a lot of great research, a lot of great innovation that needs to happen to address the needs in the next 3 to 5 years.
Michael, you're obviously working off of some of the most advanced designs, just like Synopsys and Siemens coming forward. What kinds of changes are you seeing there and what has to happen on the tooling side and the not just the tooling, but also the utilization of the tools that are there?
Yeah, so as we look out and at least along this like kind of 5-year time horizon, I mean, we definitely we've been talking about it a lot today, these like multi-die packages and solutions. That's gonna we're expecting to see much more of that. And I think that the overall system's gonna be as the other, I think Rob and Mohamed said it, it'll consist of some reusable chiplets, but I think you can also expect to see, custom silicon as part of the overall system. This overall system, the custom silicon may be very advanced, from a process technology standpoint. So everything that we're doing today to say support 3 nanometers would need to be also done to support the sub 2 nanometer or that portion of the circuitry in terms of the modeling, putting in place all the infrastructure to address the process technology challenges at that node. And then we've talked about in terms of just the overall complexity of the system. It's gonna require a lot of collaboration, both with our partners on the Foundry and in IDMs, and as well as the design teams. And there's a lot of problems that are that begin to emerge in these like multi-die types situations that you don't get necessarily the same way in a single die. For example, in terms of static timing analysis, as you start considering the multi-process aspects of the design, and you look at signals that may say span or go across chiplets, you can get an explosion in terms of timing corners, and there's new challenges as it relates to the modeling of that. In terms of, is this going to be a product that's going to be around for a lot of years versus a product, sort of might be in more of an automotive type application rather than something that's going into a product that's a consumer related product that's going to, not be existing in a couple of years versus something that's going to be a lot longer. Aging types of effects become, more important. So there's, many complexities that these forward-looking chips are going to, that from an EDA standpoint, we're going to need to address. These are just some of them.
Yeah, this has been the whole driver behind silicon lifecycle management, is that these chips are now going to be in the marketplace for, in some cases, 20 years, sometimes even 25 when you go into industrial applications. Bari, how do we plan for that? What kind of issues do you have to think of up front, and can it all be even dealt with up front, or do we have to do this as we go?
Yeah, so Ed, great question, and I think both John and Rob mentioned about resilience of the systems, and when John talked about in silicon monitoring, as you just referred to, silicon lifecycle management, starting with even in the design phase on how we add this type of in silicon monitors into the chip itself, and this with a single die or a multi-die system, and then collecting the data as we ramp up the yield, as we go into the production, and then going to the realm of in-field operation, which kind of is that in that space of software-defined hardware, where not only you are monitoring, but how can you actually optimize there? And we do, I mean, it's a similar type of optimization as you might do for even our EDA design software. You have heard about autonomous design systems, things like which will apply and optimize the design creation process. Now imagine systems like those operating on your this design, and the AI optimization systems like those operating in field, and then optimizing the various variables that allows these CPU, GPU. These are not that configurable, but you can have some level of configurability that will do this. So I foresee silicon lifecycle management, starting from the design itself, going to the in-field operation, being much more prevalent. Today, it's in its early stages. And I think that definitely is a very exciting area because it actually dovetails into this whole analytics space, which I think all the EDA software and our other panelists have all the analytics becoming the core of where your data drives your action, whether it's in infield, whether the EDA software that we are creating, we are creating the design, and that being one of the driven workhorse. One thing I felt, I know you asked the question about how chips should look like. We're talking at the system level. One of the things, I mean, as I was reading recently about IMEC's roadmap, it's Moore's law is slowing down, but it is still very exciting about things that are happening at the transistor level. And I think it is going to pose a whole lot of challenges for us, for our EDA softwares to address not only designs, but also how when the power distribution now goes into the backside, which would be one of the more common thing as we will see as the process evolves into future.
That will be an interesting challenge.
Yeah.
Prashant, one of the ways that we can actually monitor chips over their lifetime is through the idea of digital twins. The challenge with digital twins, though, is they just consume enormous amounts of data, and that data has to be stored somewhere. How do you foresee this working?
Storage. Yep. At this moment, I think it is reasonable to say that storage is going to be the #1 challenge for two reasons. Obviously, the amount of data that's required for completing a chip obviously is one thing, but then like you said, if you really want a digital twin, and if you are looking for a life cycle of 20 years or so, or even more in some cases, then all of the data that's being generated out of the design cycles has to be available in its entirety. If you really want to look at a digital twin, you cannot have abstractions. You need to have full data in high resolution be available if you wanted to do something with it, 10 years, 15 years from now. So all of that does pose a challenge, right? And as of right now, what I can say is that storage in cloud, it is going to be more expensive. At this moment, that is the case. And that's exactly what we are currently working on and trying to introduce new solutions that can have this kind of trade-off between performance and cost. There are high performance storage solutions that are available, but they come at a huge cost. But then there is also archive solutions, etc., that are also available in the cloud as well. But they are also, I mean, everything is on demand on a per use basis in the cloud. So even storage works the same way. I mean, you can put stuff in archive, but there is a cost for pulling data from the archive or storing the data into the archive. So those are all the costs over time that has to be looked at and optimized, going forward for large scale data. We are routinely, when we're talking to the customers, we are looking at 5 to 15 petabytes of data that they're looking to move into the cloud. That's already a huge challenge because there's no easy way to move the data into the cloud. If you just look at data transfer with the standard internet connectivities or even express route dedicated fiber optic connections, the rates are not as high. The data rates are not that high, and therefore the transfer take time. So all of those are the challenges, and how do you do that? Some of the Foundry customers that we are working on, we are looking at even significantly higher amount of data that's going in. So how do we manage that into the cloud, and how do we create an infrastructure so that you can have more of a policy-based data allocation, policy-based data management? When you have all of these solutions that are coming up, which can actually allow for you to do the trade-offs between cost versus performance, now you have a landscape of different storage solutions. So what we want to do, at least in the short term, is to create more of a policy-based data management systems where the customers can bring in the data into the cloud, and then you potentially have AI-enabled solutions that can do the analytics over time to kind of figure out what's your relevant data and what's not, and then be able to do some allocation internally, based on what's the performance requirement and what's the optimal cost for storing that data is. Over time, is going to mature into adding more solutions and better solutions. and also an introspection on exactly what data is actually important for you and what's not. I mean, there's when you look at any silicon design, typically you would have a lot of debug data that's written out. So there's digital twin data, but then there is a lot of analytics and there is a debug analysis data that's dumped as well. So there has to be some workflow optimization on the EDA side as well to start looking at what data are we dumping out here. And traditionally, that's been the case. It's not an issue. Dump out a 10 gigabyte debug log file that nobody is going to ever look at again, but it does get tar and GZ and put on a tape somewhere, just in case 5 years from now somebody wants to look at it. But that never happens, right? So there has to be some introspection on how the data is being generated through the whole design cycle, to optimization on that, and also infrastructure to add more and more solution to allow for that cost versus performance optimization.
You know, for years, the software guys always looked at the hardware side and said, "Oh, this is why is everything being done at such a granular level when we all are working on Python? We can run this stuff out very quickly. The software applications can be done much more quickly and much simpler. You don't have to get down to the coding at the RTL level like we do in hardware." Are we ever going to raise it up a level of abstraction? Is that even possible? Bari, why don't we start with you?
So we know of approaches, and I think you may have seen some of these RTL generators that will generate RTL from Python and Scala, and a lot of these applications are started off from the academic research. And we see some of this commercial application for creating some of the highly configurable IP blocks where these are used. One of the challenges that we see that comes with this level of hardware or RTL generator is truly in the type of the code that it generates. These codes are not the RTL that our RTL designers are very familiar with. Instead of vectorized, you will see much more, if you were to use the word scalarized, you will see this at a lower level of abstraction that becomes harder to debug, harder to take it from and let's modify it. You have to go back to that hardware or RTL HDL generator to generate it again. So there are challenges with this. There are attempts being made to produce this RTL automatically. It's hard to answer your question, Ed, whether we would see this becoming mainstream, but work is being done in this area. And there are challenges there that needs to be solved for us to move up that level of abstraction to things like Python and PyTorch level kind of things.
Was there just too much invested in the way that we've been doing it to be able to raise that up and start with a higher level of abstraction, or is it actually doable going forward in limited segments?
I think we will also need to bring other techniques like, say, formal verification techniques at that higher level of abstraction, not just the rest of the ecosystem, because I think one of the biggest challenges we try to solve as the output of that, the HDL generators, we need to stay at the input level and solve it there. But yes, it is some of the way we have done this in the past. And when you make these changes, as you said in the earlier, the verification is a large part of the time is going there, and you start making this type of fundamental shifts, that itself will take time. But I think as tools come in place to be able to verify things at that higher level of abstraction, particularly formal verification, we would see some of the adoptions of these techniques.
Well, I'm sorry, I think I wanted to get you involved in this.
Which who?
In terms of, can we raise this up a level of abstraction, or are we still going to be hampered by the fact that we have all this infrastructure and methodology and know-how in terms of how to do things at that current rate?
I'm sorry, who's the question for?
You.
Oh, okay, I missed that part. Yeah, I think so. Agree a lot with what Bari said. I think, but before leaping to Python and PyTorch, I think we're going to probably see more movement to like System C and C++. We're seeing that continuing to grow rapidly, also for hardware entry. And so we'll see, I expect we're going to see more companies adopt at this level over the coming years. And really today, Verilog and RTL is still the norm. Changing languages, it is something that's hard to displace, because I think in the tool chain, there's a lot of infrastructure, there's a lot of knowledge, there's a lot of experience that sort of gets built up around it. If you raise the language and have one tool sort of connect it, from say something like Python, to say some lower level representation, you don't necessarily have all the supporting technology in terms of verification, enabled at that same time. And I think the other thing that happens with a lot of these, earlier in my career, I spent a lot of time on the synthesis side of things, and there was always this debate about high-level synthesis and synthesis, sort of going beyond what like RTL synthesis would provide, and where the input was RTL. When it came down to really sort of optimizing for power, performance, and area, RTL was the preferred sort of representation. Some of these more abstract representations, the door was open for them, from a TAT standpoint. More productivity, easier way to sort of represent it. So this is another dynamic that is always at play here in terms of the productivity versus, the QOR and what the different solutions enable. But I think coming back to it, I'm less optimistic that we're going to see a dramatic change. Though I think you'll see some incremental advances in this area, but I think most of the language focus is going to be, at RTL, System C, C++.
John, is it just so complicated that we can't get there, or are there some breakthrough areas?
I'm less familiar with this topic. I think Michael and Bari are much more versed. But it does seem that over time that we'll get to the next level of abstraction, right? I mean, it's the same as when we went to ASIC design. But I think a challenge that I'll highlight here, to the audience, is that ultimately you look at the complexity of the designs we're doing today, and in the foreseeable future. The biggest bottleneck for us right now, I think, as an industry, is humans, is our engineers, graduating engineers, to help drive everything that we're talking about today. And so it's a worldwide challenge, and we see that it's the tremendous demand for silicon, which is driving that. And so even with more advanced methods, I believe there's still going to be a huge challenge for graduating engineers that are qualified to help with chip design.
This is an incredibly complex world we're living in, and we've just absorbed 90 minutes and just barely scratched the surface. So I find a lot of my panel discussions these days are getting more and more complicated in terms of the questions, the answers, and the interweaving of so many different things that we didn't have to deal with in the past. They were segmented into silos, but now you have to absorb all these different pieces, and that's only going to grow over time. So given the fact that we've been at this for 90 minutes, I am going to step back here, and I don't know if we have any questions, but I'm going to say my part is pretty much done.
Can I ask a question, Ed?
Absolutely.
Thanks a lot, everyone. It's a wonderful panel, and I think there's no limit to how long we can discuss. One of the things I've been wondering about is as we get into these complex, especially like 6G and edge computing applications, the analog mixed signal interfaces are getting really complex and really fast. Do we have the AMS design tools, verification tools, and the platforms that are necessary to scale up and address the challenges? We already talked about data. What about the AMS interfaces?
Any takers? Bari, it sounds like one of your areas.
I mean, I'm not an analog or mixed signal expert, but I can, speak on behalf of the company. I mean, at Cadence, this is an area where we have a lot of investment, and we work with, our customers around the world, and we have a very active roadmap, and there's a lot of technology being developed and as it relates to mixed signal design, analog design today. And we have every expectation, we'll continue to evolve those solutions to address the 5G, 6G challenge, or, like the 6G kinds of design challenges in the future. So I'm not losing sleep over that right now. I mean, there'll be a lot of hard work that we need to continue to invest in, and I have every expectation we're going to get there.
Just to add to what Michael mentioned for 5G, 6G, just like we talked about digital verification, how the problem space is getting bigger. Simulation, circuit simulation for AMS circuit simulation, not only the design aspect of it, but verifying them in the presence of digital components that make simulation. These are going to be the challenges, and simulating with a lot more vectors, at a lot longer period of time are going to be the challenges to be solved. But having said that, these are areas where circuit simulation tools, capacity, runtime is dramatically improving. There are links to the custom design software. There are links to the other analysis tools, which might be in the form of static analysis. Those are all these are the areas, hard problems to solve, but challenges, but also our opportunities for us there.
I think there's some really interesting research out there nowadays in analog as well. And it may not be precisely appropriate to 6G or to ultra high speed digital, but which basically is analog. There are various functions on, say, edge devices or these sensors we were talking about, where there's an analog object, it produces an analog signal, you just need it to be digitized. And if your choice as a chip company or designer is to say, well, let's see, I can hire 5 analog people and spend the next 4 years developing this thing, and I will get 24-bit fidelity on this analog to digital converter. Or I could try this synthesis thing that produces a, say, 12-bit version, has a higher signal to noise ratio, but is ready next week, and I'll just figure out what to do with the signal digitally. I think there's going to be a lot of that to just get around the bottleneck that you really can't afford to have. You can't afford to have your design in many cases broken by a long analog design time. So having some adequate solution may be the right answer versus having a perfect solution. And that, again, there's a lot of research out there on this topic at the moment, academically.
Okay. Well, thank you all. Great discussion. Great information here. Really appreciate the time, and we appreciate everybody hanging with us. So thank you very much.
Thanks for the opportunity.
Thank you, everyone.
Thank you.
Bye.
Thank you, all of you. Thank you, Professor Ed Sperling, for moderating this panel, this interesting panel and interesting panelists. Thank you, all of you. This is an honor for the organizing committee to have such panelists in this conference, and we wish we hope to see all of you next edition maybe, or in future events face to face, to meet all of you. It's such an honor for us. Thank you so much.
Thank you.
Thank you.
Bye. So we close actually today. We'll finish the session, and we see. Thank you for all the participants. We see you tomorrow at 9:30 a.m. Egypt time. It will be 9:30 a.m. Egypt time. Yeah, it will be 8:30 a.m. Tunisia time. The session will be an invited paper from Professor Mohamed Hassan, and don't miss the closing session. It will be the closing will be the announcement of the best paper award. So see you tomorrow, and have a nice time. Bye.